Hey everyone, in this video I'm going to continue our conversation about basic concepts in calculus. Specifically, I'm going to talk a little bit about integration. So far we've been interested in finding the derivative f prime of x of some function f of x. But sometimes we're interested in finding exactly the reverse. So finding the function f that for which f prime of x is its derivative. Okay, so kind of just backtracking the derivative process that we kind of talked about in the previous video. So in this case, we refer to f as the antiderivative of f prime of x. Okay. So the antiderivative is the or now changing the notation a little bit, the antiderivative of a function f of x is the differentiable function capital F whose derivative is f. Okay, so f capital F prime is equal to f. Okay, and we know from derivatives how to manipulate f capital F to get f the derivative. But how do you express the procedure to manipulate f to get f, so kind of to backtrack that process? For that, we need a new symbol, which we will call the indefinite, integration, or the indefinite integral. So the indefinite integral of f of x is written as integral f of x dx. So that's the integral with respect to x. And this is equal to the antiderivative of f. So there are some common rules of integrals that we can basically derive by virtue of the integral being the inverse of the derivative. Okay. So first, constants are allowed to kind of slip out of the integral. So as soon as we have a times f of x dx, we can take that a in front of the integral. We also know that the integration of the sum of two functions is the sum of the integration. So the integral of f of x plus g of x with respect to x is equal to the sum of the two integrals. We can also kind of use the reverse of the power rule. So if we take the integral of x to the power of n with respect to x, we know that in order to backtrack the logic of the power rule, we know that the integral of that has to be 1 over n plus 1 times x to the power of n plus 1 plus some constant c, because if we look at this term itself and we take the derivative and we apply the power rule, we'll see that the derivative of this term would be n plus 1 divided by n plus 1 times x to the power of n. And that's exactly n plus 1 divided by n plus 1, of course, cancels out. So we're left with x to the power of n. And c, the constant, would drop out as well. So secondly, exponents the natural exponents or e to the power of x are still exponents. So the integral of e to the power of x is e to the power of x plus, again, some constant c. If we remember from the previous video that the derivative of log of x is 1 over x, so we know that the integral of 1 over x dx is also log of x plus c. We can also reverse the chain rule, so the integral of e to the power of f of x times f prime of x dx is equal to e to the power of f of x. So oftentimes when we encounter functions that involve a product, we kind of want to bring it in a format that resembles this e to the power of f of x times f prime of x, because then we can ultimately find the derivative e to the power of f of x. And of course this kind of can also hold more generally for any f of x to the power of n times f prime of x. And in general, remember also the derivative of a log of a function. We already talked about 1 over x, but this is also, of course, more generally, if we have f prime of x divided by f of x dx, then the derivative of that is log of f of x plus c. Okay. So those are common rules of integration. Another context in which we've seen integration before is the definite integral. So before, when we talked about the antiderivative, we just talked about kind of reversing this, taking the derivative and finding the function that produces a given derivative. But we also encounter derivatives when we talk about computing the area under a curve that is described by a function. And so we can kind of derive the same rules, or get at the same rules of integrals by kind of thinking about how we can compute the area under a given curve. Okay, so suppose we have a given curve and we want to determine the area, which we call a R of a region R defined by a curve f of x. And we want to compute this area for a given interval a smaller equals x, smaller equal b. So one way to calculate the area in this case would be to divide the interval between a and b into a number of subintervals of length, of equal length. In this case, we would call that delta x, and then approximate the region with a series of rectangles where the base of each rectangle is delta x and the height is f of x at the midpoint of each interval. So this is kind of what we visualized here. We kind of divide the range of x into kind of equidistant intervals, and then compute the value of f of x for each of those midpoints. And then we can easily compute the area for each of those rectangles, and we sum up those rectangles to get the area under this curve. Okay, and of course this is an approximation, right? So of course we don't exactly get the area right, but the point is that this sum of this approximation gets more and more becomes more and more accurate the smaller this delta x becomes, right? So the smaller the interval is, and the larger the number of rectangles that we use to kind of approximate this function, the closer the result will be to the actual area under the curve, right? So in general, if we call this kind of approximation of the area under the curve using these rectangles the Riemann sum. So this is the sum of the from I equals 1 through n for n rectangles basically that have the width of delta x and have the function value at each xi for each interval, basically. So now the point is that the definite integral for a given function f, we can say that the Riemann sum approaches a limit as delta x approaches 0. So as we kind of make the width of these rectangles smaller and smaller and increase the size of rectangles to approximate the area under that function, then the limit is called the Riemann integral of f from the range a to b. And we can express this integral using, again, the integral symbol, and write this as the integral from a to b of f of x dx. And this can be shown as equal to the limit of delta x approaching 0 of the Riemann sum. And one very important kind of result is the fundamental theorem of calculus, which says that if we have the function f and it is bounded on a and b and continuous across that range, then we have an antiderivative, capital F, that is where f prime of x is equal to f of x. So we can find the antiderivative on this interval between a and b. Then the definite integral between a and b of f of x dx is equal to the antiderivative evaluated at point b, so the one end of the range minus the value of the antiderivative at point a. So in other words, to produce the procedure to calculate a simple definite integral in order to compute the area under the curve for a specific interval from a to b of a function f of x is to find the indefinite integral f of x, or capital F of x, and then evaluate f of b at the upper bound and f of a at the lower bound, and subtract those two values from each other. A couple common rules for definite integrals. The area interpretation of the definite integral provides some rules for simplification ultimately. First, it's important to remember that there's no area below a single point. So if we take an integral between a and a, the two basically the same point, then the area, of course, is 0. If we reverse the limits in the definite integral, that changes the sign of the integral. So if we so the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x with respect to x. And again, as we've seen before, the sums of functions can be separated into their own integrals. This is similar to the rules that we saw for the indefinite integral, where we have now a definite integral from a to b for a times f of x plus, or alpha times f of x plus beta times f of x, beta times g of x with respect to x. And we can separate this out into two definite integrals. All right. Lastly, areas can be combined as long as the limits are linked. So we have, if we have one integral from a to b of f of x dx and another integral from b to c of f of x dx, then this is equal to the integral from a to c of f of x dx. All right, so this was a very quick overview of calculus and integrals and differentiation. So if you still have, if some of these topics were new to you, or you didn't really remember those rules anymore, please go through those exercises, check out some of the examples in the Prefresher, and if you have any questions, we can talk about those, of course, as always, in the Q&A session. In the next video, I'm going to talk about optimization.